presentation comes to us from Kentucky in the United States. I'll be entitled Catalytic Process of Sulfated Zirconia Superacid Catalyst. And will be presented by Burt Davis.
Well, first I give away that I'm not very bright. I come to Japan to talk about sulfated zirconia since it started here, and they got started early on it and provided much of the early explanation. The reason, or a reason we got started was we found that we could control whether you get the tetragonal or the monoclinic zirconia crystal phase by the pH that you carry out the precipitation. People have had trouble reproducing that, and one reason is that you have to pay attention to the salt you're starting with. When we started with zirconium nitrate, we could make the monoclinic in a quite pure form, but later vendors, zirconium nitrate, you get only the tetragonal. The only salt we can obtain in the U.S. today is anhydrous zirconium chloride that permits us to reproduce at will which of the crystal phases we form. Once you form the precipitate, it's almost a chemisorption as you add sulfate to the dried gel. The sulfate concentration increases up to about a half molar and then flattens out, saturating the surface. The sulfate does change zirconia. If you have pure zirconium oxide, you get an exotherm about 450 degrees. This is associated with a loss in surface area. If you put sulfate on zirconia, you go to a much higher temperature, 614 compared to 450. The exotherm starts with the loss of surface area, but then becomes endothermic as the sulfate continues to decompose. This is just to show you that we do have real data for the loss of surface area for zirconia at the exotherm, and that it is associated with loss in surface area. If you look at the exotherm in air or helium, it has little influence on whether you have platinum or iron manganese or iron manganese as is used as promoters. If you carry out the treatment in hydrogen in contrast to air or helium, invariably the exotherm is 100 to 150 degrees lower, and you lose the sulfur as H2S rather than oxide of sulfur. Now, we carried this out to try to get involved in the debate, is it Bronsted or is it Lewis acidity? One way to determine acidity is to absorb pyridine. So we preformed pyridinium sulfate, added this to the zirconium oxide. The preformed pyridinium sulfate, what you would expect to form if you chemisorb pyridine on a Bronsted acid site. I contrast this to where we start out with sulfuric acid, combine that with the zirconium oxide. I show this different because it will be seen in the next slide that it is different. And then chemisorb pyridine. So in both cases we have pyridine. In one case it's preformed Bronsted acid. If we carry out the decomposition, this is in temperature program reduction and weight loss. The material that has the Bronsted acid salt, pyridinium sulfate, the exotherm occurs as though you did not have sulfate present. The pyridine is combined and preventing the sulfate from causing the exotherm to go to the higher temperature. In addition, we are desorbing mass 79, which is pyridine. So over a broad temperature range, we are decomposing the Bronsted acid salt. When we go through the exotherm, then we have decomposition. It is not decomposition of the salt, but oxidation reduction. We form CO2 and we form SO2. So rather than have what pyridine is left come off as pyridine, it undergoes oxidation reduction. When we form the sulfate first and then put pyridine on, the exotherm is at the high temperature that it would be if we just add sulfate. Again, you form CO2 and oxides of sulfur, so that the pyridine is not decomposing as you would expect for a Bronsted acid. It's indirect evidence, but nevertheless, some may believe it is evidence. Another area that there is debate is the form of platinum. I'm showing here TEM. You can use the spacing to identify platinum metal as well as zirconia. If you carry out the reduction in hydrogen to 750, the dispersion of platinum is such that you do not see X-ray diffraction for the platinum metal. If, on the other hand, you carry out, as is usually done for the activation in air, you do see XRD peaks corresponding to platinum metal. And so we believe that the platinum is present as the metal. One of the areas that is difficult to control and has caused much controversy is activation. This compares two activation procedures. One is to activate at 725 for 2 hours. In doing this, you end up with sulfur in this region. The activity I'm representing that you would get for this activation is about 75% for the conversion of normal hexadecane. If, on the other hand, we activate at a lower temperature, 500 degrees centigrade, you start out, gradually gain activity, eventually attain roughly the same activity as if you had done it higher temperature, shorter time period. The major difference is that you do not lose sulfur at the lower activation, but not all of this sulfur is contributing to the activity. Another way to look at the acidity is to use infrared and the pyridine adsorbed. Here I am comparing, starting material has different amount of sulfate. We have calcined this at 650. Depending on which batch of zirconia we start with, the maximum activity is obtained at a different calcination temperature. This is, for this batch, gave the maximum activity. We have to transfer it to the IR cell. We could then only heat to 400 degrees. So that this is different from what we're measuring activity on. In this case, about 50% of the acid sites measured by pyridine infrared adsorption correspond to Bronsted acidity. Presumably, if you had heated this to 650, you would have less Bronsted sites. But that experiment was not able to be done, and so we only got halfway answer to the question of is it Lewis or Bronsted. In this case, we have both. The question of water. If we generate water in situ by dehydrating the alcohol, it forms the olefin, but this is rapidly hydrogenated, and so it is not due to olefin poisoning. The water is a poison, and about 1/3 to 1/2 of the sulfur that is present in the catalyst contributes to the activity according to water poisoning. For the conversion of hexadecane, and this applies whether we carry this out in a batch reactor or in a flow reactor, at low conversion, isomerization and cracking contribute about equal to the conversion, but as we go to higher hexadecane conversion, cracking becomes the dominant reaction. If we compare this to higher temperature, with the sulfated zirconia, we're at 150 degrees. The data in circle is Sullivan carrying out hydrocracking at 350 to 450 centigrade, some 200, 250 degrees higher. This is looking at iso to normal for the pentane-hexane fraction. We see that the sulfated zirconia is not much different than is obtained for the normal hydrocracking. The difference is the amount of time that it takes to get the conversion. With the zeolite catalyst, it is not as active at the low temperature. Something which is still puzzling us is that as you go to higher carbon number, the iso to normal, which you would want if you're trying to make diesel, is higher with the higher carbon number than the lower. Now, if you assume the first step is making a methyl C15, if you crack at this beta position, then yes, you get a normal, and so this accounts for a low normal. But by the same token, you can crack on the other side, and so this should contribute to the iso. And we cannot, at this time, explain why this happens, but it has happened on many occasions, and so we believe it is real. If we look at the change in carbon number as we continue the reaction in a batch reactor, we see that the iso C16 is decreasing with higher conversion, and that we are shifting to lower carbon number. If we look at this in matching the products that we would expect, if you crack C16 in the middle, you should get 2C8. Likewise, you should get a C9, C7. And at early time, they match up quite well so that secondary reactions haven't begun to dominate. If we go to higher conversion, we see now the shift so that the lower carbon number in each case is the dominant product. The C9 is now less than C7. Again, if we look at typical hydrocracking, this is the classical Coonrad Garwood. As you go low conversion, you have the high molecular weight. As you continue to higher conversion, it shifts secondary reaction. We see the same sort of thing. They show if you put a good hydrogenation catalyst that you get a distribution similar to what we're getting. This is at high temperature. We're doing this at 150. And so it behaves typical of hydrocracking. There are many ways to prepare this catalyst. I'm showing 4 ways. This is sulfuric acid. As you go to longer calcination time, the activity declines, but in this batch reactor, the sulfuric acid impregnation gives the most active catalyst. The least active is when you put sulfur on with H2S and then oxidize. SO2 is shown lower here, but it is difficult in our hands to reproduce the SO2 addition, and so here you see in a plug flow reactor, or a trickle bed reactor rather, when it's made from the SO2 and then oxidized, we get the highest activity. This next slide shows this may be an artifact because there is a longer period with the SO2 of increasing activity, it declines, and then in the steady state region, it has the same activity as the catalyst prepared by the other techniques. Let me change now in an effort to try something about the mechanism. Victor has recommended this compound as a good model compound to test for carbenium ion reaction. If we look at the conversion of this, it's rapid. Part of this is because when we put the catalyst into it at room temperature, it doesn't stay at room temperature. There's heat generated, and that contributes some, but some of this is real, that it converts and then the reaction slows down. When we use this model compound, the dominant reaction is oligomerization, and the dominant oligomer is a dimer. Now, if we change from McVicker et al. Recommendation of a model compound and move the double bond from here to here, we see it's more conversion under the same conditions, and now it changes to where the products have changed to dimer, trimer, etc. One assumes in most catalytic reaction that isomerization is very easy and is the fastest reaction, but apparently with the sulfated zirconia, the oligomerization competes. Let me summarize them with just considering the mechanism. The hydrocracking has usually been viewed as bifunctional, but you operate at high temperature. We don't believe that the platinum will give the olefin to that high concentration and prefer a bimolecular chain transfer where somehow you generate the carbenium ion. This undergoes isomerization in chain. In competition, you have cracking. The cracking will produce olefin. The reason you need the metal, in our view, is that it plays the secondary role of removing the olefin and permitting this to have a long chain length before you lose the acidity. We know even after essentially all this acidity is left, if we add the olefin, the platinum retains the hydrogenation activity, and so we at this time prefer this mechanism, but next week we may have abandoned that one and switch to another one. And with that, I will stop.
Thank our speaker. Okay, we have several minutes for questions. Let me start off by asking, in your MTIR determination of the Bronsted and the Lewis acid sites, would it have been possible perhaps to have done at lower temperatures, 100, 200, 300, and then try to extrapolate up to 600?
I showed the highest temperature at the, if we only evacuated 100, then it's essentially all Bronsted acidity. And so the fraction of Bronsted acidity does increase with higher, as you evacuated 200, 300, 400. We would extrapolate that at 650, where we activate the catalyst, there would be very little Bronsted acidity. And so today we're on the side of it not being Bronsted acidity, but I say we don't hold that position too strongly, and certainly not in Japan.
Thank you. Other questions, please? Yes, please identify yourself.
Jacques Delrin from the Pacific, but from France. I was surprised following the last question that you still get Bronsted acid site at 400 degrees centigrade under vacuum.
We get which?
Bronsted site.
Yes.
Because we have studied sulfated zirconia for long, and when we degas it at that temperature, we only see Lewis sites, two types of Lewis sites. And so I was surprised by your results. I wanted just to ask you, is that the sample without platinum or with platinum?
We've done it both ways. And I didn't mention, one set of points was the catalyst without platinum. The other set of points was the same material with platinum. And the two were essentially superimposable. Some would argue if you put hydrogen in the presence of them, you generate Bronsted acidity, but at the atmospheric pressure we were restricted to by the instrument. Again, whether we put hydrogen on or not did not change the curve.
My second question, when you do your catalytic reaction, were your catalysts activated at 400 degrees under the curve?
We have found that the maximum activity depends on the batch of catalyst that we prepare. And sometimes it's 725, sometimes 650 centigrade. We activate at that temperature, remove it from the oven into the reactor so that we do not cool down before we carry out the reaction.
The reaction was performed at lower temperature anyway.
Pardon?
The reaction was performed at lower temperature.
Yes.
Your catalyst has seen the air, so he has been rehydrated.
But only taking it from the oven to a glove box. And it's done with tongs while it's still hot, so that it may be cooling quickly to the temperature, but
Thank you.
Any other questions? Everybody's hungry. Okay, thank you again.